All right. You took a quiz. I'm not going to have the sub pass it back, but I will give it back to you on Tuesday. You will have time to um, deal with the quiz scores that you got over WIN in the next couple of weeks. I think we did okay. I think that we can continue to improve. I will see a lot of the skills that we used on that quiz this half of the unit, and so just prepare yourself. Um, we'll talk more on Tuesday. Okay, so today we're going to talk about rational functions. This is section 4.3. We're kind of reeling the clock back to talk about that part of it. We sort of forged ahead to do some polynomial stuff because I feel like we need the polynomial stuff to be able to do this stuff. And so therefore, that's why I chose what we did. Anyway, rational functions are functions where both the top and the bottom of the fraction are polynomials. And hence, that's why I feel like we need some stuff about polynomials to be able to talk about rational functions. We did talk about these for a while in Algebra 2 last year. And so a lot of it will be a review, but there is going to be some more specificity, some more requirements, some more things that I'm looking for. Just we have to take another step up, right? So that's what the theme of this year so far has been, is we're taking a step up from what we know about Algebra 2 to push ourselves to learn more and get ready for calculus. So here we are. We have rational functions, polynomial divided by polynomial. Now, domain is a big part of rational functions because we know that we cannot divide by this. There's this one value you can't divide by, and it's very important that you can't divide by 0. Okay, and so anything that makes the denominator of this fraction 0 is not in the domain of the function. And that's really important because finding those spots where there are discontinuities, so this is called a discontinuity in the domain. Finding those discontinuities is really a critical part in rational functions because you have to be able to find, okay, is it an asymptote or is it a whole? So hopefully you remember those words. Let's talk about the domain of these functions because that is exactly what I just said on the last slide. So what is the one thing that makes this x equals x plus 5 can't be 0? Do you see I set the denominator equal to 0, except I made it not equal to 0? So basically that's allowing me to say, okay, the only thing that it can't be is x cannot be negative 5. So the domain of r of x is x cannot be negative 5. Similar thing here, we have x squared minus 4. And basically, we would factor this and we would say, okay, well, x squared minus 4 cannot be 0. And so then we would get x, well, I guess I could even just solve it for 0 for x, right? I could just say x squared is not 4, so then x is not plus or minus 2. So this is what I would write as the domain for s of x. Okay, similar deal here on this next one, but this is a little weird because x squared plus 1 cannot be 0. And are there any real values that make that equation true? Well, no, because x squared plus 1 is always positive. The solutions to this equation would be imaginary. And so if that was the case, then there would be no real value that goes into that function that doesn't work. And so we would say f of x has domain all real numbers. Okay, this one is super interesting because the top actually factors into x plus 1 times x minus 1. And now we have this x minus 1 on the bottom. And so you might be convinced that you could cancel those. And we would just say that g of x is equal to x plus 1, right? You might be saying, well, why can't I do that? Well, the answer is because originally the domain was restricted. Originally, the domain was x cannot be 1, okay? And so basically what I'm showing you here is that the domain, it has to stay the same even if we simplify. So if we get rid of a denominator because we're able to do that because there's common factors or whatever, we still can't cancel those. We still can't eliminate that domain restriction. That's why there's a hole at x equals 1. We're going to deal with holes in the next couple of days. We're going to talk about asymptotes a little bit today. But anyway, just be really careful. Just because you cancel something doesn't mean the domain isn't restricted. Just be careful. Alrighty. So if I know domain restrictions, I need to be able to classify them. And so today I'm going to talk about vertical asymptotes. Tuesday we're going to talk about holes, and then we're going to talk about another kind of asymptote, which is really important, but it's for the next day. Okay, so vertical asymptotes happen when you factor the top and the bottom, and then you get something that does not have a common factor. And so I can see that this polynomial on the top is going to factor to x plus 3 and x minus 3. And then the bottom, I'm going to get an x plus 3 and x minus 7. Right? No, that's not right. I'm sorry. This should be a minus 3, and this should be a plus 7. Okay, but what I see here is that these two cancel. Remember when I said you can't just cancel stuff and get rid of the domain restrictions, right? So the domain of the function is actually x can't be 3 and x can't be -7. But the only one that's actually an asymptote is anything that's left over in the denominator. So because this is left over after doing that canceling, I have an asymptote at x equals -7. So vertical asymptote at x equals -7. And what I mean by that is on the graph, there's going to be some place x equals -7 right over here where the graph doesn't touch. So this might look something like, and I'm going to have to take a guess here because I don't have a calculator in front of me. It's probably going to look something like that. All right. Okay, cool. So that's interesting because if I compare it to this other polynomial here, which is x over, and then if I factored this whole deal, I would get x plus 4, x minus 4. Do you see how there's no common factors top and bottom here? So that means that both x equals -4 and x equals 4 have vertical asymptotes. All right, so when I'm looking for a vertical asymptote, I'm looking for common factors, and I'm going to cancel those. Anything that isn't a common factor in the denominator, that corresponds to a vertical asymptote. Horizontal asymptotes are the other thing I'm going to talk about today. And so I'm just going to put this up because there's a ton of information here, and there's a whole lot of cases where we might have different types of horizontal asymptotes. You've actually seen all this information in Algebra 2 before, and so this will hopefully come back to you. Maybe not, though. Anyway, what you have to look at is the degree of the polynomials. So if I have some like x to the n over x to the m is basically what this is saying. And you're looking at how these n's and m's compare to each other. It doesn't matter necessarily what the rest of this polynomial is because the cases occur based on the highest degree. So if the numerator is greater than the denominator in power, then there's an oblique asymptote or a slant asymptote, and that's what we're going to talk about tomorrow, as well as holes. If the n is greater than m by 2 or more, then there's no horizontal asymptote. So like if I have an x to the third over x, but then there's some other stuff, then I would say no horizontal asymptote. And so that means that there's some kind of like overlapping situation in this rational function where there's no clear spot where it doesn't cross horizontally. If the degrees are equal, then you're going to take the a and the b, the leading coefficients, and you're going to do a over b to get that horizontal asymptote. And then finally, if the degree of the m is greater than the n, then that means that the horizontal asymptote is at y equals 0. So I just have an example of this here because this is a good one for that. So I'm going to start with just sort of factoring this whole thing out, and then we'll deal with the asymptotes in a second. So this goes to be x squared. Well, I guess factor out an x and I get x squared minus 9, which means that I get x times x minus 3 times x plus 3. Okay, on the bottom though, I'm going to pull out a 2x because that looks like that's common. And then I have an x squared plus 5x plus 6. And so the resulting polynomial is 2x and then x plus 3, x plus 2. Okay, so my new polynomial is f of x equals x times x minus 3 times x plus 3 all over 2x times x plus 3 times x plus 2. Okay, so what cancels here? Well, I have these x plus 3's that cancel. I have this x that cancels. And now I'm left with x minus 3 over 2x plus 2, like that. All right. And so this is sort of what I would put in my graphing calculator to see what it looks like. You could start up here too. You could put all of that in there. It's just a little easier to do it after you've done some algebra. Anyway, so then where do I have removable discontinuities? Well, the removable discontinuities are the ones that I divided out and got rid of are this one and this one. And so I have holes there, but again, I'm going to deal with that later. The one that I have an asymptote at is x equals -2. So I have an asymptote at this line x equals -2, so I'm going to draw a dotted line there to represent that. And then I have a horizontal asymptote. Because the degrees of this are the same, I'm going to take the coefficients on the a, which is a 1, and I'm going to divide it by 2. So I have a vertical asymptote here, and then I have a horizontal asymptote at y equals 1/2. So I'm going to just sketch that in here. Okay, not a super perfect graph. Otherwise, after I do this, I'm just going to go to my graphing calculator and see what it looks like. So I'm going to do that off camera because I don't think you need to actually see that. But I'm going to type it in, take a look at it, and then I'm just going to come back and sketch it. So it looks like I have a dot here. And otherwise, this graph just looks sort of something like this. For today, this is plenty. Officially, I would have to put a hole here, and I would have to put a hole at -3 as well. We'll deal with that tomorrow. Okay, you have a practice sheet where you're just doing a few of these. So you're identifying common factors by factoring out the polynomials, top and bottom. Divide anything out. Those are not something you need to deal with today. Okay. After you do that, then you'll have a simplified version of the polynomial, which is what this is. And then you can identify, okay, what are the vertical asymptotes, and then you can use the coefficients on the previous screen, or the rules on the previous screen to figure out what the horizontal asymptotes are. Then you're going to sketch them in your graphing calculator, and then just put that on your screen or on your paper. Okay, turn in your paper when you're done with it at the end of the hour, and then I will see you tomorrow. Have a great day. Thanks for your attention. Good luck.